This is going to be our last video for centripetal motion. Today we're going to start out dealing with our gravitational constant. So over here in the top left, the force of gravity is equal to g, which is a constant, written down here, times the mass of one object times the mass of another divided by the radius. If I were to just solve for the acceleration, I would just take out the mass of the second object, and so that would just be force divided by mass would give us a rate of acceleration. So to start, we're going to actually see or prove what the gravity on Earth is. Earth, everybody knows, has a mass of 5.97 times 10 to the 24th kilograms. And the radial distance from the center of the Earth is equal to 6.3 million meters. So when I plug this into our equation, I'm going to start off with our constant of 6.67 e to the negative 11. The gravitational constant is really small because you need a lot of mass in order for those two objects to have a gravitational attraction between the two of them. So here is Earth, e to the 24th, and now we divide by the radius squared. And you get an answer of 9.81036 meters per second squared. So turns out gravity is right. We still are going to use 10 just because it's easier for us and we're lazy. So that's for Earth. What if there's a second planet out there? And this second planet has twice the radius of Earth, but 3 times the mass. What would the acceleration for this planet be? Well, in order to solve this problem, if you look at our base equation up here, we're just going to take these two parts of it. So we're just going to say the mass divided by the radius squared, because nothing else is going to change. Gravitational constant doesn't change. The mass of the other object isn't even involved. So we're just going to look at these two values. So if the mass is 3 times the mass and the radius is 2 times greater, 2 squared is 4, so this is going to be 3/4 times Earth's gravity. So you always multiply by 10 in the end because you're doing a ratio of what the new planet's acceleration due to gravity would be. So this new planet just discovered would have 7.5 meters per second squared of gravity. Alright, last idea that we're going to cover is same planet. Here's my super sweet planet. And now it's got a moon out here that is orbiting my planet. Well, what's keeping this moon in orbit? Well, it's the force of gravity from its host planet. And what do we know about centripetal motion? Is equal to mv squared over r. So in order for this planet to stay in orbit, the force of gravity has to equal the centripetal force. So we can set both equations equal to each other. Big G, m1, m2 over r squared is equal to m2 velocity squared divided by the radius. Now we can start to simplify a couple of things. Since it's the satellite that's in orbit, the satellite's mass really doesn't matter. It's only the mass of my planet down here that determines how the magnitude of the gravitational attraction. So it turns out that the mass of the satellite cancels out, and here I can just move this radius over here to the top. So in the end, I have my gravitational constant times the mass of the planet is equal to the radius away multiplied by the velocity of the satellite squared. So I can manipulate that equation in any way I want to solve for the mass of the planet, the distance the satellite or moon is away from the planet, or the velocity of the satellite itself. So I can use any of those to solve for the rest. So setting the two equations equal to each other, you can solve for anything you want. All right, that covers all of centripetal motion. Good luck on your quiz.